how to do POS tagging for a particular corpus. If suppose some document corpus is given to you, and as a part of NLP engineer, you are doing syntactic analysis, and you are analyzing your sentence and taking each word of the tag as each word you are tagging as whether it is noun, verb, adjective, or determiner, or conjunction, or whatever it is. So we see that there are around 40 POS tags. There are 40 POS tags. Around approximately there are 40 POS tags. So depending upon the usage of that sentence, or usage of this word in that sentence, we'll take it one out of these 40 tags. And it's a difficult task actually. If document is big, suppose in your document, suppose your corpus is nothing but collection of documents, right? So in your text corpus, suppose there are 1 million words, and each for each word there are 40 possibilities. You have to tag out of 40. So it's a gigantic task. Like so, only computer can do, right? So if you are asked to do that, how will you do that work? So I get straight into the code action. So this particular code, warning code to avoid warning, we are importing matplotlib. We are numpy. We are importing matplotlib. Then NLP.corpus. So we have three corpus here. You see Brown corpus, tree bank corpus, and Cornell 2000 corpus. So these are the corpus. So why we are importing this? So Brown corpus, tree bank corpus, and this Cornell corpus 2000 Cornell 2000 corpus. So these are the text corpus which you have, in which POS tagging is already done. POS tagging is already done. So a lot of sentences are there in the corpus, and for each word POS tag is already written for each sentence. So some kind guys have done this POS tagging for us, and then you will ask me a question like why I need a corpus whose POS tagging is already done. So I think from basics of machine learning, we know that if we want to apply any supervised machine learning algorithm, we need the X as well as Y. So your Y is the dependent variable. So Y is nothing but your tag here. So X and Y both are needed, right? X is nothing but your word, and Y is nothing, its tag, right? So X and Y both are needed to train the machine learning model. So that's why we are importing this hand tag, which is Brown, T Bank, and Cornell 2000 corpus. So these three corpus are available in analytical library. So that we are importing because they are tagged, and we'll use them to train our model and find the accuracy. Then we are importing Seaborn, key vectors, speed vectors. Then you are getting a little bit into Keras, TensorFlow and Keras, because we'll be using RNN, a variant of, we'll be using your bivariant, bidirectional RNN. So we are getting into we'll be padding the sequence. So why you need to pad the sequences? In a sentence, you have in a corpus, in a document, you have different sentences. So obviously, each sentence will be of different length. Length means number of words in this particular sentence. Some will have 18 words, some may have 20, 25 words. But your algorithm like bidirectional RNN, it expect all the sentences of the same length. So whatever input you are giving should be of same length. So sentence 1 should also be 20, for example, and sentence 2 also should be 20. But in actual they are not. So what you do? You pad them with zeros. Like in front you add zeros. You add zeros. Suppose one sentence is only 18 words. So remaining 2 you will put 2 zeros there to make it 20. Suppose one sentence is only 20. Suppose one sentence is only 15. So you will add 5 zeros before it to make it 20. And suppose some sentence is 20, 35. So to make it 20, you will cut the sentence. So like that you have to. That's why we do padding. Then two categorical, I'll tell you when it comes. Then sequential input and model are used to make the model. Embedding I have already explained yesterday. Embedding is nothing but to represent word into numeric form. So when we represent a particular word into a vector, so that particular vector is called embedding. So So dense layer we are time distributed, LSTM, GRU I think we have already covered in deep learning lessons, and tokenizer we have already covered. The deep tokenizer we have already covered. Just to break it into tokens. Tokens means nothing but a numeric representation of words. So then we know trend test split we are importing. Then we have shuffle. Shuffle is to shuffle the data. Then see here we are importing. I will stop here. So for these four corpus we are three corpus here. These three corpus we are importing here, and we are importing them with universal tag set. So we are here we are importing and storing them in three tags. We are storing in a particular variable. So Cornell, Brown corpus, and tree bank corpus. So these are our variable which contain our corpus with tags. So when they will be printed, it will be very more clear to you. What then we do? We add all this when we are adding all this corpus. All these three corpus, whatever we imported, we downloaded, we are adding them. And why we are adding them? To increase the data for our training. It is a deep learning model. Bidirectional RNN is a deep learning model and needs tons and tons of data for training. So one corpus will be less. So we have imported three corpus and added them. So we will be using a combined corpus which is named as tagged sentences. So tagged sentences will be using as for training. So that's why we have added them, and we have added them for a simple reason. We want more data for training. So now it's a big corpus, and so we have added them. So it's a data pre-processing. So now that tagged sentences variable contains all the three corpus. So it is suppose I am printing its 11th 10th element. So from 0 to 10th. So it is 11th element I am printing. So see how it looks like. So how the tagging is done. So first tagging is your simple column. So it is tagged as dot. Then we is the pronoun. Then have is verb. No is determinant. Useful is add. So this is the hand tagging somebody has done. Painfully, they have gone through the entire corpus and this hand tagging has been done. And you know that there are some data agencies available, India also, abroad also, who take your data and generate the labels. Or some students might have generated these labels. But this tagging is done painfully by hand. Some English guy who knows the English better, good English. So they have tagged it with the hand. See, now each word is tagged here. So we'll use it for our training. So that's how it looks like. And then then tag is our Y. So tag is our target. Like that's what we want. We want to generate the tag of unknown word, right? So tag is our Y and a word is our X. So X and Y, X we are generating here. We are creating two blank list here, blank list X and Y. And then full tag, we are putting two for loops. One is for an outer for loop for text sentences, which is for corpus, and this inner for loop for sentence. So each sentence we are breaking. So see, entity 0. So entity in sentence, entity in sensor, entity 0. So entity 0 will be in X and entity 1. First, see 0 means the word. 0 means 0th element will be word, and one element will be tag. So we are taking both and appending it into X and Y. So with that we have X and Y ready here. So now our X and Y is ready. Till now, anybody has any questions? Simple. We have done. We have imported the corpus, added the corpus, and then we have broken into X and Y. It means what? We have separated words and tags. That's what we have done so far. So I take a pause here for a minute. If you have any questions, please let me know. Birds and tags, yeah. Somebody see, corpus look like this. Corpus looks like this. We have taken one particular thing and it looks like this. Corpus is like this. Word is also there, tag is also there, and they are tuples in the form of tuples. So R is a word and verb is it's a tag. Somebody has already done this tagging. And if you want the reason, we want both X and Y for our training, right? How otherwise how your machine learning model will train? So now here simple jugglery, two for loops we have done, and we have separated X and Y. So X will contain words and Y will contain tags, corresponding tags. So they have they have printed the number of words here, number of tags. So if they have printed, see the number of sentences are 72,202. Vocabulary size, so number of words are 59,448, and number of tags are 12. So they have used 12 tags here. 12 tags are there. 12 different type of, like noun is one tag, PRT is one tag, verb is one tag. So like that they have used 12 tags here. 12 or 13 tags they have used here. So that's what here. Now they have just printed the sample for X and Y. So X will contain words, right? So X first element has been printed 0 0. So see how X looks like. X is this, first is this, and Y looks like, Y are their tags. So now X, Y we have. So then we are tokenizing them. So we are importing tokenizer here, encoding them. So encoding X and Y. Yesterday we discussed that. So we did fitting and word tokenizer. X, we got the X encoded. So these words were there in string form. So we'll now get their numeric form, encoded form. Simply these were there in Y was there in numeric form, and we'll get its see simple Y also converted into encoded form. So if it is printed both see first X is printed, X first element is printed, Y first element is printed, and then their tokens are printed to contrast. Tokens are printed here. So that's what it looks like. So this is a very crude representation of X and Y in the vector form. But today we'll get more sophisticated and we'll use more sophisticated. So these are called embeddings, right? So converting a string vector into a numeric vector is embeddings, right? They are embeddings. But this vector is a very primitive, this tokenizer, it's a very primitive, it does very primitive encoding. So we'll do a little sophisticated encoding today, which is word to vec. We'll be using standard word vectors. So that's what when we come to it, I will tell you. So now here, what this code is doing is, it is simply see now the length of this Y and X should be equal, right? Like list. There should be equal number of elements in X and Y, because every element of X there is a tag here in Y. So both should be equal, right? If there are 3 words, there are 3 tags. So both should be equal, right? So anywhere X and Y should not be unequal. So that's what they have checked here. So that's what it has been checked here. So we are fortunate that there are no sentences with differences. All sentences X and Y length is equal. Then what we are doing is that we are finding the maximum length. Like our X encoded, like X encoding is nothing but your sentence, right? Sentence is encoded. Sentence is encoded. So we see that maximum length is our sentence is 271 words. 271 word is maximum length. That's what we have here. See, simple length they have calculated and the length has been printed. So maximum length in X is 271 words. So the distribution of length they have just put at a box plot. So length ka jo hai, length is a different, all the elements of X they have put find out the length, and they have done a simple box plot. So maximum words are say mean of the box plot. So around 20-25 words is the maximum average length. Then 25 percentile, and then you see there are a lot of outliers. And maximum length is 271 words. So we don't want too many words. So see, it will be a lot of computing if we take entire 271 words. So what we are limiting, we are taking each sentence only as 100 words. Beyond 100, we are cutting it off, trimming it off. So we are trimming it off, and then we are using paired sequences. So we are using a paired sequences method, like you see this paired sequences is nothing but a method available here which we imported earlier. So I will show you here. See this we had imported here. See from Keras, it is that Keras is nothing but TensorFlow and Keras is nothing but deep learning tools given by Google. So for padding of sequences, already they have a function available. So we have imported that and we have used it. See here X encoded. We have given maximum length. So maximum length is nothing but 100. And padding equal to pre. You can do two type of padding, right? Either you can prefix or you can suffix. You can use as prefix or suffix. So here we are doing as prefix and truncating. So if sentence is more than 100, a sequence is more than 100. So post truncating post means later part of that will be truncated. So if you call this function, so you will get padded sentences in X and Y. So all will be now in 100 all sentence lengths will be now 100 characters, 100 words. So all X will be 100 words, Y will be 100 words. So they have printed here, see here, X, first element of X after padding and first element of Y after padding. So see, padding has been done before. This is the padding, it is padding and it is actual encoding. So here I think we did somewhere encoded. See here, X encoded, Y encoded, X encoded, and Y encoded. Okay, so right now we are encoded sentence only. See here, encoded sentences only we are doing padding. So see, encoded sentences only we are doing padding. So here we are doing padding, right? So you notice that only encoded X and encoded Y only we are doing padding. So it's all pre-padding here. So here and Y also, you see here, pre-padding we have done and we have kept it this length, this particular entry. So there are 100 elements here. After that we have trimmed everything just to save computational effort. So if you have better computers, you can use maximum length also 271. So after that what we have done, X and Y we have equated to padded ones. So X is now X padded, Y is now equal to Y padded. That's what we have done here. So now, this is very primitive encoding we done. So primitive encoding was done using this vectorizer, tokenizer. So when we did this tokenizer when we did, so it was a very primitive encoding and we did some kind of padding here. So this is up till this very primitive encoding is done. But now today we are using professional encoding. So professional encoding means this word2vec. I think word2vec and GLOW are two schemes available for professional encoding. So this we did very primitive encoding. So little professional if you do. So word2vec, I think if I am not wrong, it is given by Google and GLOW is given by some US university. So word2vec is more common compared to GLOW. Both are used, but today we will be using word2vec. And usage of GLOW is also similar. So here what we are doing, here we had this particular thing, this binary file, Google News vectors negative, this has been downloaded from internet. So it is a standard file which has some words. It is words, like all words are corresponding to each English word there is a vector. Corresponding to each English word there is a vector. Vector means embedding. So now this is why we unfold it. Path is path. Path means this is my same folder. I have downloaded it in the same folder as this particular directory. Then I have this now. This I have got here word2vec. So this particular object now contains two things. It contains word as well as its embedding vector. Both it contains. Okay. So this I have got here. This is a standard line whenever you want to use word2vec. You have to encode it. You have to put it into a object like this. And now there is an example, very interesting example given. So here we want to find out most similar from word2vec. In word2vec there is a method available most similar. So what we are doing here, king plus king plus woman, king and woman plus woman. We are adding woman, king. We are taking a king vector and we are taking a woman vector. We are adding them and we are subtracting. We are subtracting minus man. Man we are subtracting from this. So basically it is king minus man plus woman. So what it should be? It should be queen, right? So see, it is pakka. Word to vec also gives that it is queen. Top entry is queen and its weight is 0.49. So more weight means more confidence. So see, more other entries also it is giving probabilities, but most prominent probability with 0.49 weight is queen. See, if you see, king is a vector. Vector is nothing but a numeric representation of king. If man is also a vector and woman is also a vector. So king minus man. So king is a man usually. So we are subtracting man from king and adding woman to it. So what it should become? Queen, right? So it is becoming queen. See, so it is so effective. So it is all context based. It understands. These vectors are not just like that numeric representation. They actually represent that particular word in mathematical form. They are context specific. They are context specific, and they are very much understand the meaning of that particular word. So it is mathematical representation of meaning of king. So king vector minus man vector plus woman vector is a queen vector. So that's what we expect, right? But if you do the same in these embeddings, if you do these vectors and do this, you will not get queen vector. Because these are very primitive representations. These are, if you do the same thing here, king vector minus man plus woman, and see the woman vector, it will not be there like this because these are very primitive encodings and they are not context based. So these are context based. See, is a very live example. He is a very famous and classic example. See, so word to vec is suggesting it is a queen and weight is given 0.49. All others are also given, but all given are given the less weight. Most weight is given to queen. Top entry is queen. So like that, now we are till I'll take a minute break. See, this is pretty much all of your NLP. So you use either word vector or globe model. So and one more you use bird. So bird will anyway learn later. So this is pretty much all your NLP, and you are converting word into proper professional vectors, which are context specific. So this is a classic example that it understands the context. So if queen is coming means that particular vector understands that I am a king, I represent king. This particular vector represents that I represent a man. And these particular vectors understand that I represent a woman in a language. And when I do this maths, automatically queen comes out. So that's what they are context specific and very professional vector representation. So this is pretty much all your NLP, and once you represent any word into vector form, then yes, you have to apply machine learning algorithm after that. So I take a minute break here. So any so Soman, Sahu, Shailesh or Himanshu, any question here? Is it understood? Shailesh, Dr. Shailesh? बाउंसर गया तो मैं तेरे को बाद में समझा दूंगा इसके बाद. अरे कुछ नहीं है यार, it is all these words. Suppose man is there, king is there. So Google has devised some way to represent king as vector. So king is represented as a vector which is context specific. Context specific means it understands that I am a king. I represent a king. It is just not any other Tom, Dick and Harry representation. It is a proper representation of king in vector language, vector space. Understand? And we are for every vector, for every word in English, there is a unique vector. Understood, na? So there are two schemes for that. One is word to vec, and one is globe. So anyone you can use, right? So for every word in English, there is a unique vector in that word to vec dictionary. Understood, na? Very simple. So if you do king plus man, king king minus man. So negative is man. Na? So king minus man if you do, and I add woman to it. So what is the match? You should get queen, right? So see, it is giving queen to you. So that's what is a very simple representation. So every word in English has a unique representation as a vector. So that vector is unique for that word. And Google has used some kind of deep learning methods to generate these vectors. So for a king, that vector will never change. Understood? Now that is a unique vector for that. So now, Sauji, understood? Yeah, so same thing. Mostly it is from Google, but I'm not 100% sure. But mostly it is from Google. So if somebody can quickly Google it out. Yeah, Glow is from Stanford and word to vec. Just check word to vec. Yeah. So it is google.com. So that's why it is Google News, na? So okay, so we are representing. See now embedding size. So embedding size means it's a large vector. It's a large vector. So we are limiting it to 300. We are empirically limited to 300 elements. So each vector will have 300 entries. Each word vector will have 300 entries to represent that word. Then vocabulary size. So vocabulary size will be length of your vocabulary plus 1. So that's what they have taken as vocabulary size. So if you see vocabulary size we have see here in the top. I will take you. Vocabulary size was here. Vocabulary size was here. Load data. Divide into. See vocabulary size. This is the vocabulary size. So we have vocabulary 59,448. So we have added 1 to it. So that we are taking as vocabulary size. And so now now we are taking it as a vocabulary size. Then embedding weights. So embedding weights, we are initializing a vector of zeros. So this vector will contain all zeros. So vocabulary size. So for each word, there is a vector representing 300 elements. So what will be the size of this particular matrix? Vocabulary size means rows will be the number of words, and embedding size means how many vector. What is the vector size is 300. So 300 will be its width. So vocabulary size is rows and embedding size is 300. So that is what is the size of this particular vector, embedding weights vector. And right now we are initializing it with zeros. Just initialization. Then word to ID, like it is a standard word tokenizer. So see, word tokenizer means I will take you where we initiated it. So word tokenizer, initially see here. Word tokenizer was nothing but we instantiated tokenizer and we did a fit on X. Did a fit on X. So this word tokenizer is an object which contains our entire X. Entire X it contains in the form of encoded. So it contains entire X word. It contains entire X. And tag tokenizer contains entire Y. See here, we did tokenization here. So this remember these tokenizers. So I'll take you to the word tokenizer here again. See word tokenizer, word to index. And what we are doing here is we are copying vector from word to vec model to work represented corpus. See now whatever we initialized here embedding matrix, or we initialized it to zeros. So now we want to copy from word to vec whatever our vector representation of word was there. So that's what we have copied into this matrix. Now it contains. So see, once we copy the word to vec representation into this vector, so size is vocabulary size plus vector size. So this is vocabulary size 59,449 and 300 is your vector size. So this is what we are doing here. So we are copying all the word vectors we are taking from word to vec. See, for word, in word to ID, all the vectors we are taking and copying it into embedded matrix. So word to vec we are Word to wake we have instantiated here. Word to wake we had instantiated here. That is the object. So we are using that word to wake here. Word to wake and converting all the words of our corpus. So this is word nothing but our corpus word. We are converting and copying into embedding matrix. So I think if you don't understand this code, you have to spend some time on this. So it's a simple for loop. So what we are doing, each word of our corpus, we are converting into word to wake representation by using this object, and we are copying it into embedding matrix. So that you have to see, spend it for 2-3 minutes on this for loop to understand. So that's what we have copied here. Now embedding matrix is there. It contains, see, embedding matrix shape we are taking here, shape. So it contains representation of 59,449. So this was our vocabulary size, and this is our vector size. So this is what it is, and they are just for joy they are printing the vector. So see how for these are 300 entries for word joy, English word joy. So what is word to wake? What is the vector for joy? So this is the vector for joy printed here. So these are, it looks like this. So these are entries for just academic interest. It is printed. Then I take a pause here. Is it understood, Dr. Shailesh? You have to spend some time on the code actually. If you are not understanding the exact code, don't worry. You have to spend some time on it. Okay. And later on, if you don't understand it, then we can discuss it in the next class. So what we have done here basically is embedded. Here we had initialized embedding weights as all zeros of, so vocabulary size plus embedding size. That's what we initialize a vector of a matrix of all zeros. And after that, in that particular matrix, we have copied the word vector of all our corpus. So corpus size will be our corpus size is this, and vector size is this. So that's what we have done. So now embedding weights contains all the vector representation of all the words from our corpus. So see, for a joy, suppose they have randomly taken a word joy. See how it is represented in maths. So these are 300 elements. How this is joy, representation of joy. And now Y. So Y is containing 13 categories. Y is containing 12 categories. So we are not doing any tag. For Y, we are not doing any word to wake representation. We are simply doing a one-hot encoding. So we are doing a one-hot encoding. So first we are converting it into two categorical means. See, Y will be what? Y will be your number of Y was limited to 100. See, we limited at to 100 right here. So Y was nothing here. Y was shape of Y. If you see here, shape of Y is the shape of X and Y. So this Y was nothing but 100. 100 Y the vocabulary size. 100 by the vocabulary size, right? So that's what the Y was, and then we did one-hot encoding on that. So shape of Y will be three-dimensional tensor. So this is see, now I have to look into this, that this is 72,000. So acha 70,000. This is 72,000, and this is your 59,000. So we have to see a little bit what into this. So 79,000 was your sentences, right? 79,000 were your sentences. Yeah, sentences were 72,000 and vocabulary size was 59,000. So sentences into, yeah, so these are number of sentences. So these are number of sentences. For each sentence you have 100 tags. Why 100 tags? Because initially each sentence we have limited to 100 words, if you remember. And if word was short, we did padding. So these are number of sentences, these are number of words in the sentence, and 30 is nothing but your number of tags. So it is a three-dimensional tensor. Each one-hot encoding is done for a particular Y, 13 tags are there, right? So 100 words are there, but total tag number of tags are 13. So 1 encoding will be done for 13 zeros will be there. 13 zeros, and wherever that tag is there, we'll have 1. So it is a 3-dimensional tensor. So what I'll suggest, you try to give some time. Even I took some time to understand that why the size is like this. So you spend some time and try to understand why the tensor size is coming like this. So difficult for me to explain. So this is sentence, this is your words, and this is your number of tags. So try to understand, give some time on it and try to understand yourself. If you still don't understand, then next class we can, before we start the class, we can discuss that. So once now we have, so why we didn't do any professional encoding? So we did only 1 encoding for Y to represent it in vector. We did only 1 encoding. And for X, we have done a professional encoding by using word to vec. Okay, so that's how we have done. So now we have X and Y here in encoded form, X and Y. So we have run a train and test split, and for train and test split first we have done. Test size is only 15% we are taking as test size here. So that's what we have done. And then train, once we got the train, we are breaking it into two more, X train and X validation. So train we are breaking it into train and validation, and test. So first we are breaking into train and test. So once we get train, we are breaking it into train and validation. So we have 3 sets of data set. We have training data, we have validation data, then we have testing data. So training data shapes are given here. So we have the shapes, and then so what I need to understand is that X size is, if you see X size, X is if you see X size of X. So size of X is only embedding weights. Embedding weights are only this. Okay, these are embedding. So right now we are not playing with X. So these are embedding weights. So our vocabulary size was 59,449. So there are 449 rows for each one for each word, and then this is the vector size for each word. So we are not playing with X now. So this is embedding matrix. So embedding matrix we got for each word, and X and Y size. So X and Y number of rows are 72,000 rows. X also has 70,000 rows, and Y also has 72,000 rows. So we have done this breaking, and then we simply, before I get into machine learning model, I want to take a minute break. Dr. Shailesh, you have any question? See, you don't switch off your mind. Even if you don't understand, try to catch up from where I am talking. And after that, you have to spend a good amount of time on this code to understand this code. Okay, even I took yesterday night up to 11 o'clock, and then I again got up into 5 o'clock to understand this code. Okay, so you have to spend some time to understand this code. It's a bit complex, okay? So don't switch off your mind even if you don't understand. You see small things. So right now, why this word embedding size is 59,000? Because we are playing only with vocabulary. For each word there is a vector of 300 size. So number of rows will be equal to number of vocabulary, and number of columns will be equal to number of vector size. So it is very pretty simple. Words, these are number of words, and this is the size of each word. That is what. And here Y is having 72,202 entries, means that is number of sentences in the Y. Similarly, X also number of rows will be 72,000 only. For each entry in X, there will be one entry in Y. Right? So that's what, and then after that we have done a simple train test split, and train we have done a further split on validation and train. So we have 3 sets: testing set, validation set, and training set. So we have 3 sets. So these are the size given. We have found the size. Then now we are going to bidirectional LSTM. So bidirectional LSTM is nothing but, I have the PPT here. So this is our bidirectional LSTM. So क्या होता है कि मतलब there are two RNN networks here, recurrent neural networks, two networks here. One top and one is bottom. So to one network we will feed the sequence. We'll feed each sequence now. Our sequence is 100 word length, right? We have limited to 100 words. So one sequence will lead forward, like from A to Z will feed from A to Z for the first one, and second network will feed from Z to A, reverse. And why we do that? Because sometimes what happens, suppose A to Z we are giving, then we have done encoding up to C, and then we are giving word D, and word D is dependent on some X, Y and Z. Suppose word D is dependent on Y and Z, then if you don't supply Y and Z, it won't know the context, so it will do wrong encoding. It will do wrong things. So we supply reverse also, so that while encoding the initial part of sentence, the network knows, your neural network knows that what is there in the end also. So it knows entire sentence before encoding any word. So so it understands the context before acting on it. So that is why we do once the forward feed and one is reverse feed. One is A to Z and second network we feed Z to A. So I think this very preliminary I am giving you, but for that you have to see the video which we did for this. So I'll share the video for that. So now we get into, within 10 minutes we'll finish. So bidirectional model, it is now only deep learning now. So it is a sequential, it is the first step in any deep learning model. And when we do any text processing, so first layer is usually embedding layer. So we have to give input dimension. So input dimension is your vocabulary size. Output dimension is your embedding size. So input length of the sequence is your max sequence length. So max sequence length is 100 here. Weights. So weights we are giving here embedding weights. And trainable equal to true. So we are training this layer. So what is embedding weights? So you see here embedding weights. So embedding weights is here what we derived here. So embedding weights is this particular thing we are giving here. See here. This is embedding weights. So it contains all the vocabulary of 59,000 words, plus for each word there is a vector of 300 words. So whatever word to vec we did here, now we are supplying it to deep learning model as embedding weights, then trainable equal to true, then we are adding one bidirectional LSTM layer. So what is LSTM, what is bidirectional, you have to see the videos. LSTM, there is a separate video, so you need to see that. And after that you see the last layer. So last layer we have to divide tags into one of the 13 classes, right? So you need to tell that for each word which is the tag. So number of classes are 13, 0 to 12. 13 classes are there, right? So last we have added the dense layer with 13 nodes. 13 nodes are there. So it will tell you which, for each word, it will tell you what is the tag. Each node belongs to one particular tag. So 13 nodes. So it's a simple bidirectional LSTM model. Then we employ categorical class entropy, optimizer Adam, and matrix we take as accuracy because it is not an unbalanced data set. So we take it accuracy and then we see the model summary. So see there are 18 million total parameters. It's a huge network. 18 million trainable parameters are there. Then we fit the model, just simple dot fit. It is all simple deep learning steps. So only 10 epochs we are doing because we want to save the time. But usually speaking, you should take, we are taking batch size here, mini batch is 128, epoch is 10, and validation data we are using here, see in data. So validation data we are using here. So train data we are using to train the model, and whatever results are coming, we are validating on extended YSM. So these are all standard deep learning steps. So we are plotting the results, so we can see that the model accuracy. So as epochs are increasing, train and test model accuracies are little bit matching it here. So little convergence you can see between blue line and orange line, and you can see the accuracy is whopping 99%. So we are getting a 99% accuracy with the help of, means 99% of the time we are able to give correct tech prediction. 99% of the time. So this is what we have done, bidirectional LSTM, and it is a very advanced model. Bidirectional LSTM is an advanced model. So I have here one more simple example here. Same thing here I have done with a simple RNN. See, same analysis, but here I have done with simple RNN. Same trend test done. So vanilla RNN has been done. So here, see here, we are not given any embedding. So there we gave professional embedding, right? So here we are not giving any embedding here. So I'm not giving any embedding means it will auto initialize the embedding randomly. So we are not giving any randomly, any random, simple RNN model. See here, we are using simple RNN model. So even if you don't use that word to vec and use a simple model like simple RNN, you are getting an accuracy of 95%, which is also not bad. But if you use bidirectional CNN, bidirectional one, so you are getting a whopping accuracy of 99%. So 99% of the time you are able to see. I know it is tough, and many of these things might have gone above head for many of you, because I also spent good amount of time to understand it. So you have to spend time to understand it, and tomorrow is anyway off for us because I have to go to college for lectures. So for a full day I will be busy. So tomorrow anyway is off for us. So spend some time to understand this code. And you come to the next 4th class on Thursday, then if you want, we will not keep any new thing. We will discuss only this code. Try, understand this code, spend time, and don't give up. Try to resolve things. And if you don't understand, next Thursday class, we can fully devote to this particular code, and we will not take any new things. So don't give up, spend some time and try to understand. So what we are doing here is, we are using this particular corpus. So this is the corpus, this is the word, and this is the tag. So this is word is X, V is X, and PRON is Y. So that we are using to train our model. Okay. After that, we are doing a prediction. We are trying to predict. So what predict? Suppose cancer is a word and I don't know whether it is a noun or a verb. So I want to predict with the help of my model whether it is noun or a word after training. So I am predicting